Hey guys, so today what we're going to be talking about is parabolas. Now, the parabolas that we're going to be seeing today are a little bit different than the ones that you are used to from algebra and advanced algebra. And when I say different, I don't mean that they look different. I don't mean that they act different. I mean that we're going to be looking for some fundamentally different things. So in those courses, you usually saw parabolas as something like this. f of x equals a x squared plus bx plus c, and then you might have had to set this thing equal to 0 and use a quadratic formula, or you might have had to factor this, or you might have had to graph this, find the axis of symmetry, or something along those lines. What we'll be doing today is thinking about parabolas instead as conic sections. And as you're well aware by now, conic sections a lot of the times have a vertex and also a focus as well. And that is what we're going to be focusing on today, actually, is what does the focus do in a parabola? How do we find it? And how do we think about parabolas as conic sections? Okay, let's take a look. Okay, so right here we have the general shape of one of the parabolas that you would be taking a look at. And the equation for a parabola in conic land looks a little something like this. 4 times p times y minus k equals x minus h squared. Be aware, you might also see this flipped around. You might also see it as something like x minus h squared equals 4p times y minus k. It's the same thing. Be aware that in this kind of parabola we have the x being squared, and the x being squared is the hint that this is a vertical parabola. And we will only be taking a look at vertical parabolas in this section, which is why you only see a vertical parabola right here. All right, so what does this particular equation mean? Well, we've got a few parts to it. We've got the h and the k, and the h and the k together signify this vertex right here. So this vertex is at the point h comma k. And then you've also got this number p right there, which you're not really used to seeing. You're used to seeing things like the horizontal radius and the vertical radius and the c distance, the distance from the center to a focus, and whatnot. But in a parabola, we don't really have a center. We have a vertex. Again, the vertex is h comma k. So there's no center, but there is the vertex. The p right there, what that stands for is the distance from the vertex to a focus. So that p number is this distance right there, the distance from the vertex to a focus. And the p is also this distance right there, the distance from the vertex to something called the directrix. So the focus is always a point, x comma y, that's above or below the vertex by p amount. And the directrix is always an equation, y equals something. That's always a set distance p, down or up from the vertex. So you might be wondering what the directrix actually is and what it does with the focus. So what a parabola essentially is a parabola is like a dance between these two things, the directrix, this line again, and the focus right there. So the parabola is like a balance between those two things. If I were to take one point on the parabola, like this random point right there, and then if I were to track the distance, let me try that again. If I were to track the distance that point is from the directrix, and also the distance that that point is from the focus, you would find that those two things are the same length. And as a matter of fact, that's true for any point that I could pick on the parabola. The distance between this point and the directrix and this point and the focus is the same. So what a parabola really is just a set of points that are equidistant from the focus and directrix. Now that little piece of knowledge, that's actually fairly deep, and you're not really going to be expected to use that in any appreciable way. But I wanted to at least tell you why the directrix is a thing that we talk about, because that's literally where parabolas come from. Parabolas come from this balance between the directrix, this horizontal line, and the focus, that point in the middle. And you can construct a parabola from any horizontal line and another point just by thinking about the parabola in this way. And then the last thing I want to say about this equation for parabolas is our vertex is h comma k. Obviously the p is the distance from this vertex to the focus. And the last thing is that any negative signs flip the parabola. And that's pretty much it. What we'll be doing in this section is essentially graphing parabolas and finding the focus and the directrix, just like we have for other conic sections, and also writing the equations for parabolas from graphs. Okay. Before we go on to the examples, I want to take a look at what the focus actually does. Okay. The reason why I'm giving special attention to this is because I think it's really interesting, actually. We have a parabola here, and the question that I'm asking is, what does the focus do? Well, it's actually an incredibly useful thing. So what the focus does is, if we were to take any line that's coming straight down the parabola, like this, just straight down into it, the parabola would reflect that line straight to the focus. Just like that. Kind of the meaning for why it's called a focus. So here's another line. If it helps, you can think of this as a beam of light hitting a mirror and then reflecting straight to that one point right there. Hi, Lionel. And if we were to take, like, say, another beam of light out on the shallow end of the parabola, you can see that it hits the mirror at a more shallow angle and then therefore reflects at a more shallow angle right over to the focus right there. And this is really interesting and really useful for a few reasons. You will see this sort of thing in satellite dishes, because if you have signals coming down from space and you want to focus them all in one place, a parabola is the shape that you would want to do that. If you've ever used headlights in a car before, the shape of the mirror inside the headlamp is a parabolic reflector, where the light bulb is essentially at the focus, and therefore any light that comes off of the light bulb gets reflected straight out in front of you, like that. It's a really useful thing, these parabolas, and knowing where the focus is can help us use them to solve some really interesting problems, especially in the medical field and in communications, in astronomy, in lighting and automotive stuff. It's actually really cool. All right, so let's take a look at a couple examples. Okay, so in example 1, we're asked to graph the parabola from this equation, and we're going to locate the focus and the directrix. And I suppose I'm going to do these in blue, because I usually do the focus and stuff in blue. Okay, so underneath this equation that I've got going right here, I'm going to write the general equation for a parabola that you guys saw from the first slide. that we had about conics. So this general equation for a parabola looks like 4p y minus k equals x minus h squared. If you take a look at the connections between this, you can see right away that the vertex is going to be 3, 0. Directly from reading that equation, the vertex is 3, 0. So what I'm going to do is put a point at 3, 0. That's my vertex. Next, what I want to do is find the p distance. Because if I'm finding the focus in the directrix, this p distance, this number right here, is what I want to find. If I'm finding the focus in the directrix, this p distance is what I want to find. So I'm going to take the 10, and a lot of people might think that the p would be equal to 10 just from reading that, or maybe that the p is the square root, trying to make it like an ellipse or a hyperbola or something, but that's not what's going to end up happening here. What we need to do is make a comparison between the 4p and the 10 that we've got in the equation. So what I do to find my p distance is I say, okay, that 10 in the equation, that is equal to 4p. So then what could p be equal to? Well, if I divide both sides by 4, I would get that my p distance is 10/4, and 10/4 is 2.5. So that's my p distance. And if you recall from earlier, the p distance is the distance from vertex to the focus and also to the directrix. So precisely from this, what I'm going to do is build where my focus would be and also where my directrix would be as well. So 2.5 units up, so I go up from the focus 2.5 units, 1, 2.5, okay. There's my focus, is what that's going to be, and then down 2.5 units, 1, 2.5. So my directrix is this horizontal line right there. So from looking at this graph, I can say that the focus is at the point 3, 2.5, and the directrix is the equation. It's not a point, it's a line, so it's an equation. The directrix is y equals -2.5. Again, because the directrix is a line, not a point. And then to actually graph the parabola between these two things, what I would do is essentially just sketch a parabola to the best of my ability. You should kind of know this, that the larger the p distance, will mean a wider parabola. So just kind of keep that in mind if you want to draw things semi-accurately. Then the last thing I want to say here is there's no negatives in this equation. So what that means is that the parabola opens upward. Okay, so that's all the important stuff. Just to recap, we started with this equation, and I wrote the general equation right underneath it. From there, I was able to get the vertex of 3, 0, and I plotted that over there. And then I said, okay, 10 has to be my 4p. So then my p distance, I can solve for that, and I got 2.5. And then from 2.5, I kind of went, okay, this parabola opens up, so the focus should be up from the vertex, and the directrix should be down from the vertex. And then I drew in both of those, wrote a point for the focus, and a line for the directrix, then sketched a pretty parabola in between them. All right, let's take a look at the next example. Okay, so this parabola is a little bit different. The first thing I want you to notice is that we've got a negative sign here. So that means that this parabola will open down. So that is one thing that we will want to keep in mind. So let me write the general equation for a parabola underneath this. So we have got 4p times y minus k equals x minus h squared. Now right away, hopefully you can kind of see that I've got a couple differences between these. I've got numbers on both sides in this equation, whereas in my standard form, I don't. I only have the 4p on the side with the y. So maybe what we should do is make this standard form happen first. And what I'm going to do in order to do that is divide the negative 2 over to the other side. And that's going to get me negative 14 y plus 5 equals x minus 1 squared. Okay, so from this, let's decide what our vertex is. So the vertex of our downward opening parabola should be 1 comma negative 5. Let's go ahead and graph that right now. Over 1, down negative 5. So 1, 1, 2, 3, 4, 5. Okay. There is the vertex. Now let's go in and find the p distance. So to find the p distance, I'm going to make the same equivalency between the 4p and the negative 14 as from before. So 4p would have to be equal to negative 14. So then what I can do is divide both sides by 4, p equals negative 14 over 4. And that would be negative 3.5. Okay, so my p distance is negative 3.5. That means that my focus is going to exist above or below the vertex. Think about it for a second. Remember, our parabola is opening down, so where would our focus be? Above or below? And why? Okay, so the focus should be below the vertex in this case. If our parabola is opening down, we want the focus to be within the parabola, within that curve. So I'm going to go down to 3.5, so 3.5 units, and there's my focus. So there's my p distance right there. And then for the other direction, 1, 2, 3.5, and I'm going to draw the directrix in there. So my focus then is at the point 1 comma, and then I started at negative 5 and went down 3.5 more units to find the focus. So this would be equal to 1 comma negative 8.5. And then my directrix would be in the opposite direction. But remember that it's just a line, so I get to write it as y equals, and then negative 5 plus 3.5, which would be negative 1.5. Okay, and then just because I like doing this, I'm going to draw this parabola in here. So my parabola is opening down again, And the focus is pretty far from the vertex, so that means that this is going to be a pretty wide parabola. Ooh, that does not look nice. You know what? That's okay, though. It's important that we tried. All right. Okay. There's that parabola. I can't emphasize enough that what you'll want to do first is trying to make sure that you make a comparison to the standard form like this, and then reading what the vertex and the p distance will be from that standard form. All right, so in this equation, it has us, in this example, it has us go backwards from a few pieces of information. We're going to try to find the equation of a parabola from the vertex and also from the directrix right there. Now the two things that I'm going to do first is I'm going to plot those in the graph. So the vertex is 2, 0. And the directrix is y equals negative 3.5. So negative 3.5, of course, is a horizontal line down here. It's negative 3.5. And what we're going to do then is think about what the form of equation for the parabola would have to be. So if my vertex is right there, and my directrix is y equals negative 3.5, I automatically know what this p distance would be. And then I also know that because that p distance is between the vertex, v, and the directrix, that if I go the p distance in the other direction, I would get the focus. So therefore, this parabola has to open up like this. So let's start writing the general form of the parabola equation. So I would want to write 4p y minus k equals x minus h squared. And let's see if we can do that. So this parabola opens up. Which means all positive numbers, no negatives. And let's take this opportunity to just plug what we know into the equation. I know that my p distance is 3.5. And I also know that my vertex is 2, 0. So that means the k has to be 0 and the h has to be 2. So really, all I have to do here is write 4 times 3.5 times y equals x minus 2 squared. And if I were to simplify that a little bit, what we would end up with is 14y equals x minus 2 squared. And there we have it, the equation of a parabola that has a vertex of 2, 0 and a directrix of negative 3.5. Remember, it's really important that you try to plot these things first. Plotting these things allowed me to actually visualize what was going on. And that really helps me understand that this parabola was going to end up opening up, and also let me visualize what the p distance was as well. And once I knew both of those parts, writing this equation was actually pretty straightforward. All right, let's take a look at the last problem, which I would consider maybe not a qualified problem. I mean, it's a word problem, but parabola word problems don't end up too difficult, which is kind of nice. Okay, so what this says here is that there's a radio telescope that has a parabolic dish with a diameter of 100 meters. The collected radio signals are reflected to one collection point, called the focal point, being the focus of the parabola. Okay, so right here, we've got the focus of the parabola, and it says the focal length is 45 meters. And what we want to do in part A is write the equation of this dish. So let me draw a picture here, because I am just like addicted to drawing pictures. Okay. Oof, that is not a good parabola. Let's try that again. That's not it. Okay. All right, that is a better parabola. We're going to go with this one. Okay, so this parabola, this parabolic dish, has a diameter of 100 meters. And then we've got a focus in the middle that is 45 meters away from the bottom of the dish. So that's the focus. So we might as well then call this point right here the vertex of the parabola. So what I'm going to do then is I'm going to notice some things about the way that I've drawn this. So this particular parabola, it opens up. The P distance is 45. And also, we could pretty much call the vertex 0, 0 if we wanted to. And I do, actually. So what we're going to do here is just jump right to writing our equation. Our standard form parabolic equation is 4p times y minus k equals x minus h squared. And if I just use all of this information and plug it into this equation, we get something that's really easy to write. So 4 times 45 times y minus 0 equals x minus 0 squared. So in the end, we end up with 180 y equals x squared. Okay, there's our parabolic dish equation. And the reason why this would be important is if you need to manufacture this, like construct it or something like that, you might need some sort of mathematical description of the shape of this dish so that you could plug it into a piece of software that might be in charge of the manufacturing process, or the design software, the CAD software or something like that. Okay. And then this last part, what we want to do is find the depth of the dish rounded to the thousandths place. Now the depth of the dish is not just 45 meters. We want to find the depth of this dish given the fact that the whole thing is 100 meters wide. And what we're looking for then is this distance from the top of the dish to the vertex. Again, if we know that the whole thing is 100 meters wide. So let me redraw, well, what I want you to do for a second is, in order to answer this question, let's consider this point right at the edge of the parabola. If the vertex right here is 0, 0, then this point, this green point on the edge of the parabolic dish, what would its x-coordinate be? Think about what its x-coordinate would be, maybe using the fact that we have 100 from end to end. Okay, so the x-coordinate of that particular point would have to be 50. And now we don't know the y-coordinate, but if we did know the y-coordinate, that would end up being the depth of this dish right here. So what we're going to do to find the depth is take our equation from up here and use the fact that the x-coordinate would have to be 50 meters. So let's plug that information in to the equation. 180y equals 50 squared. So what we can do is we can square 50, get 2,500, and then we get 180y on the other side. Hi, Lionel. So in order to solve for y, we would divide both sides by 180. And let's see what we would get for that. I'm going to grab a calculator. Why don't you do that too? All right, and what I ended up getting is 13.889 meters. So that's what my y-coordinate would end up being. Now that might be a little bit unexpected because I bet that you were expecting that the depth of the dish would be more than the focal length. But hopefully if you think about it, this sort of makes sense because if you've ever seen a satellite dish, like the kind that you might have for TV or something, the dish itself might be really shallow. And then the receiver would sit like way out here. And that's a pretty common construction for any sort of satellite dish, is that you want the focal length to be pretty far away, and then this dish can be wide and collect the data, the transmissions, and then focus it directly to this point. But anyway, that is parabolas. All these problems, except for the first one maybe, are pretty solidly proficient. You might see some completing the square in the practice problems too, but you would expect to see problems that have to do with graphing parabolas on the formative in a couple days. You would expect to see problems that have to do with writing equations for parabolas on the formative in a couple days. And you might possibly see a word problem. You might also possibly see one on completing the square. So these things might be split in basic, proficient, and then the qualified between those two. Okay, that's what I've got. If you guys have any questions, please feel free to email me. You know how to find that. It's alex.murphy@isd477.org. I will be checking my email as much as I can. Please do email me if you've got questions, and please do math. You know that this is the only way to get better at it, is to just try them for yourself. And it's parabolas, luckily, I think that these parabolas are kind of cool. There's a lot of cool uses to them, and once you do get a couple under your belt, just like ellipses and hyperbolas, they're not that bad. All right, thanks guys. Have fun.